Hey guys, welcome. We're talking morning 2 of EXAG. Today we're going to be starting off with PCG as our initial topic. It's sort of a perennial favorite. One bit of just admin stuff so you know in advance is in the back of the room there are these sheets with a menu on it. You can order a box lunch, so if you don't want to go out to the Mexican restaurant over in the golf course, there are other options. You can get a Cobb salad, fish and chips, or the Tavern burger, among a number of other options. They may or may not be reasonably priced, depending on your definition of reasonable. They're in the back over by the water. So other than that, though, we're just going to start out by covering a couple of talks on procedural content generation. So our first talk is from Sasha. The second talk is actually a remote talk, so we'll be playing a video, and then if Skype is cooperative, we'll be fielding questions remotely via Skype for the second one. Great.
Hey everyone, so I'm Sasha. I'm with the School of Interactive Computing at Georgia Tech, and I'm part of the Entertainment Intelligence Lab. And I'm here to talk to you about mixed reality and procedural content generation in video games. So I add the games because it says in video in honest candidates. So mixed reality is already being looked at as the next new innovation and the newest, the biggest change to come in the gaming industry in the last 30 years. When you look at real life, nothing really replaces a live experience where all your senses, your visual, haptic, audio, olfactory, and so on, are fully interacting in a real-time live world. And with the advent of mixed reality in the future, there is a chance that virtual reality might actually pale in comparison to mixed reality as a disembodied experience. And with the introduction of the new head-mounted displays from Magic Leap, the HoloLens, and so on, there is a chance that now more than ever, we can have experiences that actually change and adapt to the user's environment. And so this is some of the work that our team at the Entertainment Intelligence Lab has been doing. And a big shout out to Kristen and Kyung as well for all their help in the project. And so what really is mixed reality? So mixed reality can be defined as the merging of real and virtual worlds and elements where you can interact with both physical elements and digital elements in real time. And so that's still kind of confusing. So if we actually look at it, mixed reality can be defined on a virtuality continuum as ranging from real environments, which we're all in right now, to augmented reality environments. Augmented reality is basically the real world is augmented with virtual elements. So you've seen this from Pokemon Go all the way to the new HoloLens games and experiences that are out there. There's augmented virtuality. Augmented virtuality is where you're augmenting the virtual world with real elements. So you could think of this as anything from using real world physics to modify gaming experiences to actually just as simple as streaming maybe a real video into a game. And finally, you have completely virtual elements, which everyone over here, virtual worlds, which everyone here is already familiar with. So mixed reality is defined as not completely real and not completely virtual, but anything in the middle over there, between those two spectrum, where you can interact with both the virtual elements as well as the real world to kind of create a feedback loop of sorts. So if you look at the current games that are out there, mixed reality games have been kind of progressing over the years. So with the new HoloLens, we saw card-based or marker-based games like Yu-Gi-Oh! Later, last year, we saw Minecraft being demoed at E3, where a single table was used to project a diorama from Minecraft. You could kind of lean in and then look at all these elements actually moving around in holograms. After that, we actually saw the real world and the virtual world a little more correlated, where now you have Young Conquer, which was released, where Conquer actually responds to the edges of tables and surfaces and kind of does a like falling off the table animation if he's coming too close to the edge. And here in Young Conquer, the user actually handles the entire experience, where Conquer moves to wherever it is that the user is looking. And so you could actually decide where you want to go in a level. And so that's actually a lot different from Minecraft, where you would just like tap and zoom in and bomb things. And then finally, now you've reached Project X-ray, which is kind of like a laser tag of the future, where they actually use the walls in your room to simulate like realistic looking holes from which machines are kind of projecting and coming out of and then shooting at you. And so this is just like a peek at the potential of procedural content generation in mixed reality environments. But what if you wanted to play Mario in your own home? And what if your home doesn't look as nice and neat and easy to figure out as, say, the Project X-ray example? So let's take a general home or a living room. And this is not at all what my living room looks like, so I didn't want to take that picture. But let's say we first look for interesting surfaces in the room. Can we now play Mario on these surfaces? Or suppose I now notice that there aren't any red cushions or there isn't too much red color in the environment. And so now I can maybe have the user bring red pillows or red coffee mugs into the environment and maybe have procedural content generation health points awarded to them or armor generated for them if they're near red obstacles. Or even if it's raining outside, maybe if it's raining outside, you have Mario kind of slipping on surfaces which are like puddles on the floor now in mixed reality. And so we really want to see a closer tie-up between these real environments and the virtual environments. And so how do we go about doing that? And it gets more complicated than that. So for instance, let's assume that we don't really have a static environment where we're just like interacting with the world around, but we actually now have a dynamic environment with a dog or a cat. And I don't like cats, which you can tell from the mean looking one there, or like a baby that's actually now walking around the world. And so now you have all these other constraints about not just what areas are changing, like the cat drops a bottle over, how does that change your game, but also, okay, you want to completely avoid the crib in the center of the room and play around that. And so how do you kind of handle space-based reasoning like that? And so we posit that there is a need for artificial intelligence and specifically procedural content generation within a mixed reality environment because, well, with spatial reasoning, we already went through some examples with that. There's also a more increased dependence on the real environment to change your game and figure out how that looks like. There's a lack of control, which we already spoke about with the cat knocking over the bottle. And using contextual knowledge about the world or the extent of your world knowledge to actually model changes in your game. And so that's kind of where our story starts. So we had the motivating factors, which I already spoke about, where we have adoption of the new head-mounted devices that are coming out and the increase in the mixed reality experiences that are out in the market, and the need to actually tailor these experiences beyond the simple spatial and computer vision techniques more to the user and to your environment. And so that kind of led to our methods, where we looked at design considerations on what kind of games we could create and what kind of heuristics we could look at which would actually affect the real world and the virtual world and tie them up. And what would the minimum requirements be to like generate a game in mixed reality with respect to the preliminary surface detection and environment detection and so on. And then the actual generation of procedural content generation. So for everyone in the room, although I'm sure everyone already does a lot of PCG work, procedural content is the use of algorithms to automate production of various aspects of the game. So that could be anything from terrain to level generation to weapons, enemies, and so on. And what we're trying to do is to allow different players to experience maybe either the same room or multiple different rooms or different configurations of your furniture as a different level and change the way that they look at the game at different levels of complexity. And so these methods basically lead to the outline of our talk, the broad outline of the talk, which we'll go through one by one. So first is design considerations. So now we have to start looking at what are the types of games that would be playable in anyone's bedroom or anyone's living room. And so when we look at the objectives that we had, there's so many to consider that we thought for the scope of this talk, we would kind of restrict ourselves to the two which seemed most unique to the mixed reality environment and as different from virtual reality as we could. And so the first one we looked at is how to adapt to virtual to physical surroundings or environment constraints. and then how to adapt to players moving around their world. So till now with virtual games, you have players sitting in one place, huddled over a computer or with their Xbox and playing, and now they have the additional challenge of not just navigating in the virtual world, but also in the real world. And so some of the environmental factors that we looked at were, how do you deal with cluttered environments or sparse environments? And so you can actually see the image at the bottom on the left, well, right for you, is the actual image of our lab. And so we were trying to figure out what kind of game we could simulate within like those in that particular space. And we also had to consider the context of the environment. Like, are we looking at like a living room game or a kitchen game? Because that could actually change maybe enemy generation and so on. So in a living room, you can imagine different enemies. In a kitchen, you have knives thrown at you. And then the replayability of the game. If you pull a chair out or add another chair in, how does that kind of change everything? The next thing we had to look at was navigation factors. So with virtual reality, once PCG is generated a level, that's it. The player plays through it. The player has no say in the generation of the level. You could use player modeling to actually change the difficulty of the level, but the player doesn't have direct control over the environment that's being generated or the world. In mixed reality, you actually have to kind of look at that. How do you plan that the player will just change everything, or the player might challenge the PCG algorithm by not putting any furniture in or putting just a single table, or you tell the player that door is locked and I still kind of walk through it because I can. And so we had to look at that. We also had to look at how reachability became an issue. So to give you an idea about reachability and vision of the character, so if you have virtual characters around the environment, we now have the added advantage that we can move the characters, the human players around the environment as well. And so how can we come up with a game where the users kind of have to be within view or within reach of a virtual character, so that we can now kind of tweak a few parameters around and have push for the users to walk a lot more or walk a lot less. And so we came up with two prototype games, Mario and Lemmings. Both traditionally, Mario and Lemmings have research done in PCG to create levels in a completely virtual environment. And so we added all these considerations that I just talked about, and we came up with some designs that are more specific to our world. So they're loosely based on Mario and Lemmings, but a bunch of elements are changed around. You should also note that currently we don't have a mixed reality device, and so all these have been simulated. And so we can run you through the simulations and show you how it seems to be working. You can also look at this on the Oculus right now, but I'll get more into that. So with mixed reality Mario, we came up with the concept where, well, the floor is lava, so Mario is not allowed to fall down. And he has to deal with enemies that are more obvious or more natural to a mixed world or a real world environment. So we have books that kind of smash down on you, or pencils that follow you and kind of poke you around, and you have to avoid all these characters while navigating through the space. And so the user kind of has to walk around and follow Mario slightly in order to keep Mario in view of any issues that come up. And with Mario, we had a strictly constrained linear track that we were generating, which was allowing us to control the virtual player's movement very, very detailed way, even along like the backs of furniture. This allowed us to actually adapt for difficulty or eventually generate rhythms and change the length of gameplay. With mixed reality Lemmings, we had a slightly more loosely constrained path. The player was directed as to which surfaces to travel to, but within the surface, we allowed for continuous movement. And so the way that we achieved that was, well, players use jump pads and virtual boxes that they put in the environment to redirect the Lemmings around the world. And so in this particular game, reachability also becomes a really big issue, where we have to make sure that the human is actually close enough to the table to put a box onto the table. And so for the remainder of this talk, we're going to focus on the Lemmings game, and so talk about the parameters one by one as they apply to that. So let's look at the level generation preliminaries that we have to look at. So we had to apply spatial reasoning to some extent to kind of understand the world that we were in. And so our pipeline started with mapping the environment. So you walk around with a Kinect 2.0 with Kinect Fusion. Then playable surfaces were detected with like surface detection algorithms that we wrote. And then we kind of generated a graph which could then be navigated and sent to our PCG algorithms to come up with an interesting game. So just to give you an idea of what the architecture looks like, you have the Kinect 2.0 processing the world that you just saw. It generates a 3D model, which currently, since we're simulating the game, we send to Unity so that you can kind of see what the actual sofas and so on look like in the real world. We also do surface detection, which then sends playable surfaces to an AI server, which we've written in Python. Once level generation is completed in the server, the elements from the level generation are sent to Unity. And so now Unity now knows what the playable surfaces are, where the character is going to fall off, or what the platforms or walls look like, which I'll come to in a few minutes. So just really quick walk through what our process is. This is the real environment. When you scan it with Kinect, this is kind of what you get. Once this is done, we look at surface detection. So surface detection has wavefront object files that the Kinects generate, which have a list of vectors and vertices and vertex normals. And so we get rid of all the negative Y normals, which is basically the underneath of tables, because we don't want Mario walking upside down. We get rid of walls, because again, we're not having characters right now that walk on walls. And then we find connected components, which kind of look like this, concave surfaces. Once we have these concave surfaces, so this is a 2D top-down view of the exact same game area, which will just be easier to walk through different graphs in 2D for now. And so if this is the top-down view that we've graphed out, we make a game world graph where each node is a surface that we've identified as a playable surface, and nodes are connected by edges. If the virtual character can jump from one surface to another without the need for like a bridge or a virtual platform. That's about it. And now we can go, now that you've understood the world and the setup that we have, we can jump into the procedural content part of the talk. So to give you an idea of what we're talking about, we first had to design heuristics that took both the real world and the virtual world into account. Then we kind of used a generate and test method for procedural content generation that looked at all the possible tracks through the world and evaluated them using our heuristic. And then once we had a route through the world, we generated accompanying virtual assets on the world, which are walls, platforms, enemies, and so on. So some of the heuristics that we shortlisted were the length of the route or the gameplay, the player's actual physical movement through the space that he had to keep, the difficulty of the track, so number of enemies, where these enemies were placed, and so on, and a proportion of surfaces used with respect to all the surface area available in the world. So if you have a giant table, how do you make sure you use the entire table or maybe come back to the table later? And so for the scope of this paper, I'm going to talk about the first two, which is the length of the route of the gameplay as well as the player's physical movements, and kind of show you how it all ties up together. So length of the route, actually, so if you look at the 2D world, you can actually see two different routes possible through this world based on what heuristic we gave the algorithm. So we have a 0.9, which is longer routes are weighted more heavily. And so we have this as our heuristic, the one on the left. And on the right, you see actually a shorter weighted route, which is just maybe two surfaces that the player has to move the lemmings on. And so this allows for controlling the length of the gameplay. And with player physical movement, here's an example of what we're doing there. So we have used an RRT, or a rapidly exploring random tree algorithm, to predict where the player can move within the environment. So the reason we used an RRT is because it allows us to go through continuous space and map where the player could move. This is more or less what our RRT looks like when you're actually generating it. It starts with a random point, which is where the player is currently, which we're getting from the camera's current position, or the HoloLens current position when you're actually moving around the world. And then it starts exploring random points next to it and kind of expanding until it reaches points close enough to our RRT heuristic. So the heuristic that we've set up is the point that it has to end up in has to be reachable so that the player can kind of lean forward and touch the, or like interact with the frontmost lemming, but also has to not be in the table because we don't want the player or the camera to kind of walk through tables. And so this is kind of what you get from the original RRT paper, where we're trying to actually expand through different continuous spaces. So it should give you kind of an idea of what our algorithm looks like in the background. So RRTs don't need any connections to be made within the continuous space, which makes it really fast. Our RRT actually runs 100 times and gives you like an average of the path in real life. And so the green dotted line is actually the player moving through the path. So if we say that the player has mobility issues and we don't want the player to move around a lot, then you see with the 0.1 heuristic, we're choosing maybe just moving from one surface to another where the player just kind of puts one box and you're at the end of the game and you're done. So a smaller path would be generated. Whereas if we say we want the player to walk around a lot, it chooses a sequence of surfaces to be traveled where the player is actually walking around in a very, very confused manner. So you could kind of imagine maybe starting here, going here, having the lemmings walk here. And then you need to kind of reach this surface eventually, so you can walk around again. And so this is an example of what the RRT came up with when we said we want a really long path. And so how do these heuristics tie up with each other? Well, we have a combination of heuristics that we're looking at. Each of them are normalized to give outputs between 0 to 1. And we have a weight that we ask the player to provide at the beginning of the game generation, where you say, okay, I want long paths, I don't want to move a lot, I want the game to be XYZ difficulty. And so we favor heuristics that return values closer to what the player seems to want. And so longer paths are returned if you ask for long paths. And the way we do that is we basically look at the difference between the absolute value and subtract 1, and then we sum it up. And so if you look at these two possible games that have been generated, so you can see the one on the left, we ask the RRT to give you kind of a medium length path for both the virtual character and the player to move around on the surface. And so this is what it came up with. And the one on the right, we said we don't want the player to move much. So we gave it a 0.2 on the heuristic, but we want the virtual character to move a lot. And so it's kind of interesting because what it did is it took the starting position of the player. The green dotted lines again is the player, is the human walking through the environment, and the blue is where we're expecting the lemmings to be moving. And so what it did is it kind of mapped the player walking into the center of all the surfaces, and so the player can now kind of turn around and have access to every surface around him, allowing for the player to move very little, but the virtual character to kind of cover everything around him. I will come to the black lines and the red lines in a little while when we come to the rest of the ones. And so this is what our output from our heuristics actually look like. So you can see with the half, 0.5, 0.5 weight for human and virtual player, you actually get like a medium length path, like only 4 surfaces being looked at. And when you actually weight the other way, you have this really long path generated. And you can actually see how that same path in the 0.5, 0.5 had a really low weightage, and how that kind of changes around when you look at it and change the heuristics a little bit. So we have some other random interesting solutions where if we say we want really long paths for the virtual player and the humans, and so that's kind of what the RRT outputted. Or if we say we really want short paths, in that case it kind of just lets you walk to the middle, to the center table over here, put a box, and then you're at the end of the game. And so now that you kind of have an idea of what our heuristics look like, we can talk about the generation of our virtual assets. So with virtual platforms, the concept is there are some spaces or some surfaces that are too far for the virtual character to jump on its own. And so with virtual platforms, we're allowing for bridges between these spaces. And so you can direct the Lemmings or Mario onto these bridges and then jump from there. And so those are shown up in the graph as the black lines between the surfaces. So in this case, it's actually, this is a lot lower than this. And so there's like It's in 2D, so it's very weird to imagine, but it's actually going upwards as a bridge. And here, these two surfaces have been detected as too far from each other, and so the black line over there shows you how they connect. And with virtual walls, what we realize is that, well, no matter what long path we wanted the human to take through the space, humans tend to try to do the easier way. And so we wanted to see how we could actually direct the humans into taking the path that we want them to. And so what we did is we created virtual walls in the application, and so the lemmings die if they touch the virtual walls. And so those are actually shown by the red lines here. So you can see that maybe left to themselves, the human might have tried to go from this surface to this one. And so we kind of want them to be restricted to going around. And so we created a red, like a virtual wall here, which shows up as an invisible wall in mixed reality. And the same over there, where you don't want them to directly jump between surfaces, you want them to go around. So those were generated. With virtual enemies, we really had to rethink what enemies meant in real world environments, in living rooms, what do you expect to see versus in kitchen environments and so on. And I'm running out of time, so I'm just going to jump into future work. So with integration, in the future, we plan to look at integrating it with an actual mixed reality device so we can evaluate what these look like in real environments and how players actually deal with these deal and interact with these virtual elements in the real world. Okay, that happened. Sorry. We also have to evaluate our choice of interactions and choice of heuristics, which is something that we will be doing. And just to get an idea of where the field is going right now, so there is a need to generate and design players and levels that match not just the environment, but the player's interaction with the environment. Maybe you make a game that involves a player moving furniture or kind of shuffling the lemmings around by putting his hand out, having them jump there and pulling them to another surface. And so these are all things that you can now consider in a mixed reality environment. Players can really affect the generation of levels. So again, we've talked about rearranging furnitures, introducing new elements into the environment. Another thing that's interesting to consider with mixed reality is how do you actually handle challenge progressions across environments. So I start a game in my living room, and now how am I actually going to compare my skill set with a player who has a completely different living room, or a completely different bedroom, or a dorm room, or people walking around and a dog. And so all these progressions also are going to have to change, and the way we think about them have to change over time. And so you can almost see a feedback loop being generated where you challenge the player in one way, and then the player says, okay, fine, let's see, you design an interesting game like this, and then pulls a chair away, far away, or starts removing furniture. And you can imagine getting into your house the next day and your kids have basically destroyed your living room because they're trying to see what is the one game that cannot be generated or cannot be played, or they set up the living room so that their friends come over and then they just absolutely will be defeated by the game. And so these are dynamic environments that we all have to kind of account for in the future. With respect to heuristics, we've only looked at very few. We've looked at just the player movement and reachability that we've covered today. But you could think of eye tracking in a completely different way. If a player keeps looking at the clock, maybe you end the game sooner. If he keeps looking at coffee, maybe coffee becomes a new power-up. So we have to start thinking beyond machine learning and surface detection and trying to really understand the environment that the player is in. And so to end, I'm just going to leave this really nice quote up here from David Holz, where reality in the future is really going to mean something very different from the reality that we have right now. And so how are we actually going to be part of this reality? How are we going to change and design our games for this world? And that's it. Thank you. So questions? I'm just going to have these running in the background.
Cool talk. Have you thought about sort of issues of when you put this on a real device like HoloLens? You know, I've used the SDK or anything like that. Presumably, you're getting a lot of data in incrementally. You're not getting scanned the whole time. And I assume it's like slam to figure out what you want to time. Is that going to affect any of this particularly, or do you think you can?
So the really nice thing about the HoloLens and Magic Leap and all these devices is they kind of handle this for you. There's a lot of surface detection that we won't really have to do anymore once we move to a mixed reality device. So one of the things that we will be doing is from the HoloLens, getting an idea of what the surfaces are, and then where we actually want, then the AI system still runs in the background, which is really fast and just figures out where we want the player to go next. And what surface, and so HoloLens also does registration, Magic Leap and HoloLens, both of them, they do registration for us, which means it knows that this table is this table. So I can leave the room, come back, and it still knows that this is the same table. And so we don't really have to worry about the fact that we stop a game midway, we come back, it handles all that for us once we've done the planning for the game.
It may be a prerequisite step where you have to say, we're going to ask you this program.
It handles some amount of the dynamic environment problem, so that kind of takes it away from us. We are interested in so many different problems of the procedural content generation, we really don't have to worry as much about the surface detection part.
I like that it modeled the generator considered where the player would be in order to interact with things. And I saw on the chart that it certainly considered the position, but also considering the orientation also. So that it knows about swiveling back and forth versus looking in one place.
No, and right now it's not considering orientation. We've kind of assumed with the RRT that the player is always going to be facing the direction he's moving in. So we haven't really looked into, well, the player having to turn around. One thing that we have done with the surface generation, with the game generation, which I haven't talked about, is so we know where you're starting in the room, and we know that we don't want you to run looking for where the lemmings are going to be spawning. So at the moment, the lemmings will kind of spawn in the surface closest to you. And there's like a little, I don't know whether you can actually see it. There's a tiny little animation that shows you where they're going to start spawning. Let me see. I think it's in this video. And so we have you looking around the first time. And so as soon as you finish looking around, there you see that little wormhole-ish thing. So that's where the lemmings are going to start spawning, so you know where they come from. But after that, we can assume that you're always looking in the direction that that you're walking. And the RRT considers reachability all around you, which you saw from when we didn't want the human to walk. So, any other questions? Yeah.
Just a comment. I mean, I find this stuff really interesting. But you might think about, rather than trying to support existing game genres like platform games and so on, think about how can we design new game mechanics that fit your AI. Like have a game where the characters are running around and you have to alter the environment in order to block them or enable them, or what have you. And I know that's not exactly a PCG. Well, actually, that might be a PCG problem, but a really, really hard PCG problem.
So that's actually kind of where we're hoping that this field will go, where we stop thinking about like existing games. So we started with existing games because we wanted to see what are the differences we would have to consider now that the environment is kind of changed into looking at the real world and kind of figuring out the interaction with the virtual world. But eventually, I'd really love to see games like the one you're talking about where it doesn't even have to be a game, honestly. I could be walking down a street, and if I'm at a signal, maybe you just tap your device and you play Mario on all the cars that are passing. And since the device can actually do some amount of object recognition, maybe when the the walking sign comes back, it stops the game for you automatically, even though you're not looking at it. And so there's like a whole world of mixed reality stuff out there, which would be pretty fascinating to play with.
I think at this point we're going to go on to our next talk. So let's thank the speaker. So for our next talk, our speaker actually couldn't make it in the end due to logistics. So we have a video of the talk, and then after that we'll switch over to a Skype call to handle some Q&A back and forth with the actual people who did it. So Tommy sent us the video because he's, talk, and then after that we'll switch over to a Skype call to handle some Q&A back and forth. The actual people who did it. So Tommy sent us the video.
Go to sleep.
Oh, yeah.
Boop.
All right, so we are going to get the show back on the road, starting with a section, as always, very descriptively titled Theories, but we're really just talking about papers that start to really take a step back and look at some of the problems we're tackling as a whole, either through building systems to address these, or to start to build out frameworks to understand the space. And so with that, I'll hand it over to Adam again.
Thank you. So hello, welcome. I'm Adam Summerville, and I'm at the Expressive Intelligence Studio at UC Santa Cruz. And today I'm going to be discussing procedural readings procedurally. This is work done in conjunction with Chris Martens, who unfortunately couldn't be here, Michael Mateas, Joseph Osborn, Sarah Harmon, Noah Wardrip-Fruin, Jhala. Okay, so before I actually discuss proceduralist readings procedurally, I'm sort of going to give away the why we're doing this, why do we care about this. And so the punchline is automatic game generation with meaning. A number of people have looked at approaches for doing automatic game generation, but I'd say it's been a pretty limited subset of people who have tried to generate games automatically that carry with them some sort of meaning. Most notably, I'd say Mike Cook with Angelina. I believe this is Angelina 2. I could be wrong. If Mike's on the stream and starts tweeting furiously, we'll see that I'm wrong. But so Angelina, at least this version of Angelina, would be given a certain theme or topic, and then would try to pull images to evoke that theme and incorporate them into a platformer. And then the other one that I think is of note is Game-O-Matic by my trainer Brian Blackford, Michael Mateas, and Ethan Bogos, which tried to sort of automatically generate news games where a user could come in this case, this is a game that I, the user, made up, and just find relationships between different entities. So I had that a cat eats a mouse, and that the dogs chase a cat. And then we'll try to generate games that carry with it that meaning. And you can sort of re-roll to try to generate new games that also carry with it that same meaning. So the way that these have sort of approached the problem is that they take a fixed meaning. They take, the user specifies a meaning, and then the process generates a game. But this is, and not to speak ill of them, but it's been sort of a guess and, not even check, but a guess and hope that the game actually carries with it that meaning. There's no way of testing that the game that they're generating actually carries that meaning. So the goal of this work that I'm presenting today is to close the loop and to if you're given a game, can you then automatically derive the meaning of that game? Again, so this is all for automatic game generation. So the eventual goal that we hope to have is that given a fixed meaning, you can generate a game, and since we've closed the loop, we would verify that that game actually has that meaning. Original goal. Okay, so what I'm going to do is first go over the proceduralist readings framework, and then I'm going to discuss how we do it procedurally, and then finally conclude. Okay, so proceduralist readings, also from Trainer et al. It was a framework to sort of semi-formally derive meaning of the game. Game scholars have been finding meaning in games for a lot of different ways, and the idea was to sort of formalize this and have a framework by which you could compare two different readings of a game. A close reading of a game to say well, this one accounts for this phenomena and this reading doesn't, so maybe this is a more complete reading because it accounts for more phenomena found in the game. And so I'm going to sort of build up a graph that will sort of describe the framework, and I'm going to be sort of carrying this color coding through the rest of the talk. So the game, which will be things in green, is made up of the definitions. This is their term. And so definitions can be thought of as the stuff of a game. It might be what we will refer to and they refer to as entities. You might think of as Mario or a Goomba or a breakable brick or what have you. What they term as meters and what we'll refer to as resources. It might be thought of as a scalar value, like number of lives or time left in level or points or something. And then some other definitions like timers and some other things. But that's just the stuff, and games have more than just stuff. You know, they have the rules governing the stuff. You know, the mechanics that define the game. You know, how do these things actually interact? You know, you might have that when the player presses A, Mario jumps. When the player lands on a Goomba from above, the Goomba disappears. You know, how do these things actually interact? Again, this is just the sort of core portion of the game, like what you could expect to find in the ROM or what have you. But you know, there's more to games than just the ROM. You know, players actually play them. And so this framework builds off of the MDA, the Mechanics, Dynamics, Aesthetics framework of Haneke et al. You know, and so dynamics is sort of defined as like when the player is actually doing stuff. Like, what is the player going to do? Like, what is the actual loop of the game looking like when a player is inserted? You know, the mechanic is that player presses A, Mario jumps, but you know, the player will press A to jump to cause Mario to land on the Goomba. You know, this is the actual sort of dynamics of what's going to happen in the game. And then, you know, those dynamics carry with them sort of aesthetics. How do they make the player feel? What is this sort of general feeling of the game, of these dynamics as they're playing? Like, you know, we could have, you know, gray squares doing all of this and still have the same mechanics and dynamics, but, you know, the aesthetics of that will feel very different from Mario hitting a Goomba. And, you know, and these aesthetics are informed by, like, the theming of the game. You know, so, again, as I said, gray squares, not gray squares. And so all of these then flow into the meaning of the game, the dynamics, the aesthetics, the theme. And then, you know, you can sort of also then chain meaning off of itself and have meanings build up, you know, sub-meanings leading to sort of larger meanings of a game. And then all of this is informed by the sort of fuzzy culture blob. We all carry with ourselves our own cultural context. We all are raised into our own cultural context. And these can, you know, change how we would approach the same, you know, base game. You know, in Western culture, red might mean anger or danger, but in other cultures, it might mean happiness or wealth. So the same, you know, base game might be interpreted differently based on the different cultural context. And so again, I'm going to be keeping green as game, orange as sort of derived information, and blue as culture, sort of moving forward. And so for this talk, I'm going to be doing a deep dive into a game that they used in the Proceduralist readings paper, which is the free culture game, and play it right now. So for those of you who haven't played the free culture game or played it a while ago and don't remember it, it's a free culture game, a playable theory. This area is the common. Here, the knowledge is cooperatively created and shared. Using the cursor, you can distribute the knowledge to the people in the common. This is the domain of the market. Here, the knowledge is commodified and sold. The vectorialist is the device that controls the market. Its goal is to copyright ideas and create scarcity in the common. Access knowledge in the common will stop producing new ideas and turn into passive consumers. Consumers who don't receive commodified knowledge will return to the common. Their mission is to protect free knowledge and liberate all the consumers from the domain of the market. Okay. So the way the actual game plays, I control the cursor. I sort of can push these little idea blobs around and touch a producer. Touch a producer, they get absorbed. The vectorialist occasionally decides to eat stuff. The little dudes and dudettes are peeps. I guess I should borrow Ian's term. You know, going and huh?
I stole it from Rob Zubek.
Well, we all steal from. So anyway, that's what this game is about. We take the ideas in the common. And so anyway, as we see that I'm you know, only hurting to this peep, that peep is getting greener, but the rest are, you know, slowly getting grayer and grayer. Imagine this peep is going to be the first to leave the common. Let's see, probably. Oh, yep, there, pop out. Okay. So that's the game. This is what we're going to be using going forward. So just sort of try to keep that in mind. Oh.
Is that a speed run?
That was a speed run, yeah. high level free culture gameplay. Okay, so this is the Proceduralist reading from the paper by Trainer et al. I'd recommend reading the paper. I'm not really going to go into it, but just sort of give a high level overview of this type of stuff. Okay. the definitions, what are the entities in the game, the cursor, the producers, etc., the meter, ideas absorbed, the goal, turn or be green, the rules and mechanics, producers spawn new ideas, the vectorialist pulls in new ideas. The dynamics, because producers create new ideas, the player's goal is to turn everybody green, the player just forces ideas. And then we build up through up to the final meanings of given dynamic 1, aesthetic 1, theme 1, we lead to meaning 1. New ideas are hard to control, but with careful attention, they will benefit everybody. So this is the type of work that we're trying to do, procedurally. So, this is our goal. We want to derive the dynamics, aesthetics, and meaning from the base structure, mechanics, and cultural context. To do this, we needed a language to cover the game in enough detail, and we need to be able to infer properties over this language. And so now I'm going to be discussing the language that we created to do this, which is Cygnus. So Cygnus is built out of, it's operational in Klingo, so it's an ANTS prologue 2.0 predicate logic form. So this could be read as that of things type entity. One of those things, there's a unique identifier that we're just going to say as consumer. There's no actual semantics to consumer there. It's just that that's a unique identifier. Wherever we see consumer, it's going to refer to that class of entities. Similarly, for a resource, we have that there is a resource, ideas fed, and then things like that there's the timer, consume ideas. That there's a timer for the vectorialist that determines when they're going to start consuming ideas. So here are all of the definitions found in the free culture game. So the way we define mechanics are that mechanics are some set of preconditions that are associated with some outcome, and then there are some set of results from that outcome. So a precondition is defined as the condition, and that leads to that outcome, and then the results of outcome action. I'm going to sort of keep this sort of syntax highlighty thing for the rest of the talk. So this is, for those of you not familiar with ASP, a capital letter sort of denotes that it's, and I'm going to mangle the term, and Adam will hit me later over the head with a ruler or something. But it's essentially a free variable that is going to be done, there's pattern matching that'll be done on it. We'll have to, it's not the ground truth. It's going to be found in the ground truth by other things, but we're sort of doing some sort of pattern matching. So a precondition is some condition. So for instance, one of the ones we have in the language is overlaps. So overlaps, so the new idea is overlapping with the producer. That leads to the outcome of learn, which then the result of learning is that ideas absorbed increases by 1. And then another result is that the new idea that was part of that overlapping is deleted. So this is how we define the mechanics in Cygnus. Again, as I said, these things have no, sort of unique identifiers have no semantics to them. Learn is just so that we have a nice thing to read in our own code, but it could easily be replaced by banana, and the system would work just fine. Assuming that ASP or Klingo works fine on Unicode and does not work fine. We could write banana then, but have it not look quite nice. Anyway, so now I'm going to go through, we have the language, and now I'm going to go through 3 case studies of readings of the game that were done automatically as part of our system, and sort of drill down through them to discuss how it's done. Okay, so one such derived thing would be that the goal of the game is to maintain ideas absorbed. So how do we know this? Well, the one way of determining the goal of the game is that we have a precondition. We have that precondition, the condition of it is a low threshold on the thing that we're trying to maintain, ideas absorbed, and the goal, the precondition leads to an outcome that we are trying to prevent. So in this case, we have that if ideas absorbed is less than or equal to 0, that leads to the outcome convert producer. And so we see here that we have a low threshold of less than or equal ideas absorbed that leads to the conversion of the producer. We know that a priori that the goal is to prevent the conversion of a producer. So we have a sub-goal that we're trying to maintain the number of ideas absorbed. So the way this is going to work is that we have to have everything sort of ground out in either the cultural knowledge of the game that we bring, or the base structure of the game itself. And so we still have something here of the orange low threshold. So we have to sort of fully follow that branch down to fully ground it out. Which leads to that a low threshold is that there is a less than or equal to of some resource, and this resource exists in the game, it is absorbed, and some threshold of which there are sort of predefined thresholds that we might find. And so we see here, it's ground out, we have this reasoning done. So now I'm going to go into a sort of much more complicated one. I'm going to go down one branch of it, because if I tried to do this, we would be spending way too much time doing this tree. But that's that the player will do, so we're trying to do some sort of the dynamics of that the player will try to create the condition that the cursor is near a new idea to create the outcome of pushing the idea with the cursor. So the player will do sort of reasoning chain is that there's a condition and an outcome. And so that outcome must be favorable. The player must be able to create that condition, and that condition must enable that outcome. So we have the condition, or that the cursor is near a new idea, which then leads to the outcome of pushing an idea. So we're only going to drill down the top branch here. At each point, we hit a break room to go down the top one. So we have that pushing an idea is favorable. So why do we believe this? So one such way of determining that an outcome is favorable is if that outcome enables another outcome, and we know that that outcome is favorable. So we're sort of chaining up different outcome favorables to say, well, this will lead to another outcome that I know to be favorable. In this case, pushing an idea enables the outcome of learning. Remember, it's the idea touching one of the little green peeps. So again, how do we know that pushing an idea enables learning? So one such way is that if an outcome enables a result, and that result enables the other outcome, then we would say that the first outcome enables the second outcome. Okay, so how do we know? And so in this case, it's that pushing an idea enables the new idea moving away from the cursor, and that result can enable learning. So how does that outcome enable? How does pushing an idea enable moving away? Well, the simplest such way is that the result of that outcome is that leads to that action. That's what we have now ground out in the game. We see that, and so we have fully ground that one branch. We'd have to do this for the rest to be able to make that inference about the sub goal of the game, but I'm not going to do that right now. So now I'm going to do one more case study that incorporates the cultural knowledge. And so this is that the outcome is better than another for a given entity. So in this case, we have that for the producer, learning is a better outcome than forgetting. So how do we derive this information? So outcome better than is that there's an entity, one outcome, and another outcome. And then we have that the connotation for a given outcome, or for a given entity at that outcome is one connotation. The connotation at the other outcome for that entity is a different connotation. And then we have the cultural knowledge that connotation 1 is better than connotation 2. So we have, for the producer, the connotation at learning is better than the connotation at forgetting, because the connotation at learning is life, and the connotation at forgetting is death. Now again, this brings with its own cultural context. We maybe in Western society would generally say that life is better than death, but this is not, the Goth cultural connotation. So, you might imagine flipping this and coming up with a very different reading of the game, but we're just going to assume the standard life is better than death. So how do we have the connotation that the producer at learning has life? So one such way is that the result of that outcome is to set the color of the producer to some color, and that the connotation of that color is life. And so we have, again, the cultural connotation that green is nature and life and vibrant. So we have, therefore, that the connotation for the producer by turning more green is more life. Similarly, for the forgetting and death, we have that the result of forgetting is that we set the producer to the color gray, and gray is lifeless and decay and death. So we have that the connotation for the producer at forgetting is death. Okay, So I'm going to do, we did a deep dive into the free culture game. I'm going to do a couple sort of high-level ones that we did for other games to sort of show some of the breadth of what this can do. I'm not actually going to drill down or anything, but just some sort of high-level one. So we had Pong, and one such thing that we had is that Pong is a symmetric competition. And that's because that there is a sort of symmetry between that one of the goals is to limit the computer score, and the goal is to gain the player score. And those are symmetric in that there's a high threshold for both, and that the result of one of those high thresholds is loss, and the result of the other high threshold is winning. So again, this is just to show you some of the other types of things. We applied it to a bunch of different games. Another such one is Kaboom, and that we had that Kaboom has a feudal outcome, and that's because it has monotonically increasing difficulty, and that's because the bomber's speed monotonically increases, and that the bomber's speed is tied to difficulty. You know that the bomber's speed is tied to difficulty because the bomber is an antagonist, because the bomber creates bombs, and bombs are harmful, and you know that bombs are harmful because the bomb touching the screen bottom decreases the number of lives. Lives being less than or equal to 0 leads to game loss. So again, the system will produce a lot of different readings of games, just trying to give you some idea of the breadth of types of things that it can produce. So again, to sort of now resurface from the deep dives, this is all for the goal of doing automatic game generation. So what we have done in this talk is shown that holding a given game fixed, we then derive the meaning. The end goal and what we're currently working on is to hold the meaning fixed and generate the game. And so hopefully we'll be presenting that work in the nearest future. So to conclude, we proceduralized the proceduralist readings work of Trainer et al. We implemented a new game-centric domain-specific language of Cygnus. We authored the rules to derive dynamics, aesthetics, and meaning from the fixed input of the game's definitions and its mechanics. And then used an ASP solver to generate interpretations of games. Thank you.
So I noticed that when you're building out the framework for Cygnus, you seem to have 3 moving parts. The first being a high-level domain-specific, game-centric at least, that can be applied to a wide variety of games. But you also have a lot of cultural context that you're bringing in that you may or may not want to swap out depending on what sort of cultural context you want the generator to situate the game in, and the definition of the game itself such that the ASP can actually reason over it. How large are these different chunks relative to each other? Is there a lot of just is most of the work done such that I can take in a new language, a new game very easily, or build a new context very easily?
Yes. I mean, for some definition of very easily.
Yeah, obviously.
Yes, the games tend to be relatively compact, maybe say 20 to 30 lines of code per se. The interpretation rules for the game are in the hundreds to thousands. The cultural connotations, again, on the order of maybe 60 to 100. We had a pretty small cultural. I imagine could blow up. For what we did for this work, it was relatively small. But yes, these sort of authoring of game and cultural context are definitely a smaller percentage than the rules governing it.
So assumably for this paper, the examples you gave just sort of as a group wrote up cultural knowledge. Probably, I would guess, if it's only 60 to 100 lines, you just gave the cultural knowledge you thought to be relevant to this game.
So for the cultural knowledge,
right?
Yeah,
so,
I mean, so it's not just for this game, but it's we looked at color and came up with a bunch of different connotations for different colors and different comparisons of different connotations. even if they were not necessarily present in this game. But,
Sure. But in the future, to be able to procedurally read an
Any
unknown
arbitrary
game,
game, yeah.
you may need significantly more cultural knowledge. And cultural knowledge you may not have access to, so you can just use your own intuition. So where does that knowledge come from?
What do you mean if you don't have access to?
So say I'm interested in how someone in a specific city in Southeast Asia would read this game. I don't have access to the cultural knowledge there. Where do I get it?
It's an authoring problem. It would require you talking to people in that city of Southeast Asia to determine their cultural context. I mean, yeah, I don't think could derive that automatically. So.
When you run your system to generate interpretations, does it spit out all possible ones, or do you run a time to sample them, or what?
So right now it is.
Multiple interpretations, I don't know.
Yeah, so you could have, so it'll come up with one sort of exhaustive set of things. There is the possibility, so it'll give you one sort of, giant set of things. It's not just sampling or producing one at a time, or it's producing one, but it only ever comes up with one. There's no sort of as of right now, no choice that one meaning might preclude another, although that could be a possibility for future work.
Many years ago, some ideas that this project was forming, we had this idea of the elegance of an argument, but how do you know an argument is elegant? It's well, maybe compact ones that don't have unnecessarily long reasoning chains, or touch 50 areas of knowledge only to build some inference that you would. In that case, of all the zillions of interpretations you would make, you would say give me the most elegant one, or if somebody doesn't like something, you would say disallow that argument and then construct another argument for the same meaning that doesn't go through the same path. You know how you would do that?
We certainly could do the latter, and we could do the former as well. I mean, it would require some additional authoring of the framework, but I feel confident that we could try to go for parsimonious meaning derivations and favor those, or disallow longer ones if a shorter one exists. And similarly, it would just be coding up if I don't like this, meaning that don't allow that one. But
I kind of have two related questions. One is you've built out this theory of here's how people interpret.
Mm-hmm.
Do you have any thoughts on how you might try and evaluate that? And this is particularly toward the number 2 question, which is intertwined, is written a lot of these rules. How robust is the system to I took out this one rule? Is it completely unable to produce meaningful interpretations? So kind of this coupled question, how do you know your framework is capturing the kinds of aspects of interpretation and meaning games that you want?
Yeah, that's a good question. It's actually a sort of a current avenue of research is trying to do sort of user evaluations to say we believe that this is a good reading of the game. Is it do people agree with that reading of the game? Or what are aspects that we would want to have to fully cover, or a sufficiently small space? And would probably take general AI to fully cover all possible interpretations of the game. Probably not going to solve that in the next year and a half. To say well, what is the what things can we even actually measure in people to say this game makes them this, the meaning of this game is because this feel is anxious or something. Can we actually measure that from people to say that the game that we're generating does that? Or so there's definitely a user evaluation portion that we're considering right now. Haven't taken any sort of concrete steps on yet. And then the latter was to know how much we have of full coverage. Was that sort of what you're saying? Robustness. So robustness, you mean you said if this one rule is missing, how well?
Yeah, taking the human analog, right? It's we don't all share the same set of ways of drawing inferences. We certainly don't share the same sets of background cultural knowledge, etc. So if you ablate small chunks of that,
It would depend. I mean, I think it would be very dependent on what chunks you're ablating. Things like the sort of boilerplate of like, well, this thing enables this thing. Like, if you got rid of that, then a whole host of things. Like if like that's sort of the base machinery. If that was gone, then a lot of different meetings would But if it was like a single high-level interpretation, like symmetric competition or something, was like, well, you wouldn't have that, but like that's sort of the highest point, and not many things would be building off, or that's a very high point in the inference chain. So the lower you are, the more the ablation would hurt, probably.
You looked at argumentation theory?
No.
Neither have I.
Ha! How's that one?
I just wanted to toss out there that one of the future work directions that I would love to have conversations with folks about are how to move towards dynamic analysis for inferring properties. So right now, what we're doing kind of the equivalent of like static analysis in software engineering. And of course, there's a lot of there will be many game properties, both sort of emotional, emotions that will create the layer, et cetera, that you actually have to simulate the game in some way. And of course, I know people in this room, a number of people have done generators that have kind of evaluation of the generated games, but that's typically in context where you're trying to say, oh, I want this game, I want this to be a two-player symmetric game that's fair. And so your dynamic evaluation is to like do a bunch of rollouts to see if people win and sort of roughly equal amount of time to players. A little less clear how to do that dynamic evaluation when it's more sort of aesthetic properties and meanings that we're trying to get out of that dynamic evaluation. But we're well aware that like we're kind of getting to the limits of what we can do through static analysis.
Okay.
This is the recording. I don't know if you told me that. This is recording? This is recording. Oh, okay. It's been our second. So I have it on here. Should I just plug in and?
Yes.
Right there? It is online somewhere.
yeah, send the link out.
The Q&A will be us.
I can stand up and call you guys on Skype.
And Skype in if you prefer.
I think that would work a little bit better. And then I'll let you know that I have questions.
Got it.
Be a little,
Hang up, and then you guys can come back.
more aesthetically.
Yeah.
Okay.
I'm just gonna stick this thing near your
Okay.
Mac output. Unfortunately, we don't have any aux.
HDMI is not gonna pick it
Oh
up.
yeah, that will be
Too
fine.
magic with the
That'll be
It
fine.
should be an HTML.
I have it here.
Oh, okay. Direct.
It's the newer ones.
What do you have? You have a mic?
Yes.
The dinosaur.
There's some dongle they had up here, so I assumed it must be required.
Gotcha.
All right.
Let's test the audio quickly.
Hello.
Okay. Hello. Cool.
Hi.
I guess that's it.
That was a
Drop the
recording.
mic. We're done.
And let's full
It's
screen.
I mean, strong start.
Yeah.
Strong finish. Well, you're ahead.
I like rooftops.
Okay. So we'll play this and then we'll pop back up for Q&A.
Yep.
Okay.
So that's the introduction.
Thank you.
Hello, everyone. My name is Ben Samuel. I'm a PhD student in the Expressive Intelligence Studio at the University of California, Santa Cruz. And on behalf of myself and my colleagues, James Ryan, Adam Summerville, Michael Mateas, and Wardrip-Fruin, I'm here to talk to you today about computationally assisted performance. I'm not here. I'm attending a wedding between these two very lovely people. But these two very lovely people, my colleagues, James Ryan and Adam Summerville, should be here and hopefully be available to answer any questions you may have. So the plan is to begin by providing a little bit of the motivation that helped inspire this work, briefly going over the source experience that we drew from to develop our taxonomy and process we then follow to create and validate our taxonomy, then an analysis of the roles that taxonomy helps to reveal, and finally a brief exploration of potential design spaces that our taxonomy helped highlight. So let's begin with our motivation. Computationally assisted performance is a burgeoning area for artificial intelligence applications and an important stepping stone towards deeply interactive, generative, and personalized interactive narrative experiences. So there are many dramatic experiences being created across many disciplines, including games, traditional theater, and a blurry place between the two. And these experiences share dramatic properties, but our community lacks a consistent vocabulary with which to speak of these experiences. And this is what our proposed preliminary taxonomy hopes to address. Namely, there are two chief goals that we believe such a taxonomy affords. The first goal is that such taxonomy allows scholars to be able to disambiguate the properties of existing works in this burgeoning area of computationally assisted performance. And the second is that it facilitates the recognition of areas of the design space that remain as of yet unexplored, providing inspiration to create experiences that break new ground. This work itself was inspired by many others, including taxonomies in other domains and proposals for future directions of AI-based game design. So to help us develop our taxonomy, we examined a range of existing work that could be considered performative in nature. For many of the pieces we examined, we treated them as exemplars of a given type of work. The pieces we looked at can roughly be divided up into a few different categories. The first category is traditional, non-computationally assisted performance, or pieces where technology does not play a substantial role in the experience as it is traditionally performed. These include classic plays such as Hamlet, Auguste Boal's Forum Theater, with the most famous form of his Theater of the Oppressed, where trained actors perform scenes which are then re-performed with spectators assuming the roles. Also, immersive theater pieces such as Sleep No More, where audience members are free to follow actors as they choose, as the actors themselves traverse a multi-story building as they follow a scripted performance. Our next category is what we've deemed fully computational experiences. Here, technology is the primary mode of interaction, and it includes such works as Mateas and Stern's Azad, where a drama manager interprets the parsed text and actions of the player to select narrative beats, which a context selector sequences to bring two virtual agents to life. Jason Rohrer's Sleep is Death, which provides digital resources for two players to tell a story. And BioWare's Mass Effect, a Western role-playing game where players assume the role of a character who must speak with, fall in love with, and fight with characters across the galaxy. Our next category, computationally assisted performance, describes works which represent a middle ground between traditional performance and digital storytelling. Bad News is a game developed by myself and my fellow authors, and is frankly one of our inspirations for making this taxonomy in the first place. Here, a world generator simulates nearly 150 years of a small American town. Players explore the town, engage in conversation with NPCs that are portrayed by a live improvisational actor who is adhering to the character's simulated personalities. All the while, a wizard is updating the simulation based on player actions, and lots more besides. Seance is another game which involves a live actor where three players are brought into a physical tent and slowly discover their backstories and relationships with a deceased friend. An unseen wizard triggers mechanical cues to make everyday objects appear magical. In Coffee, A Misunderstanding, audience members are brought on stage, their dialogue determined by other audience members through selected choices determined by a host. And finally, we sort of have a catch-all category to place pieces such as group live-action puzzle games, such as escape rooms, tabletop games like Dungeons & Dragons or Vampire the Masquerade, Nordic LARPs like the Monitor Celestra, and Pretend Play, all of which have varying degrees of performance. So armed with all of these source experiences, we attempted to find commonalities between them to form our taxonomy. And that taxonomy is what we wish to talk about next. So our taxonomy is predicated on the belief that the instances in the design space of computationally assisted performance can be demarcated by the distinct roles of their performers and consumers. So for each role in the experience, we measure it across 4 dimensions. That means that, for example, in Hamlet, the actor playing Hamlet and the actor playing Gravedigger #2 have the same role of actor, as they both fulfill similar functions. So we identified 4 dimensions that demarcate the roles found in our source experiences. Each role is measured by how it scores across these 4 dimensions on a continuous scale of 0 to 5 for each dimension. And that is the degree to which the dimension is activated in the role, ranging from a very high score of 5, to a score of 0, meaning that the dimension simply is not present in that particular role. Our 4 dimensions are performance, computational, consumer, and agency. So starting with the first dimension, performance speaks to how noticeable a role is at the surface of the experience. A high score speaks to the role being central and visible, so a role that involves speaking or typing lines, gesticulating, or otherwise being seen by an audience in some way would all lead to a higher performance score. As would a higher degree of characterization, such as a role with backstory, goals and aspirations, and personality would score higher in the performance dimension. Though other critical contributions to a piece's execution, such as Facade's content selector, can also perhaps be considered forms of performance. A low score implies that the work of the role is not seen directly by the audience or has minimal opportunities for expression. The second dimension is computational, which speaks to how computational the role is, or the degree to which it is embodied or informed by a machine. A high score means the role is performed entirely by a machine. A low score means the role is either mostly or entirely performed by a human. A medium score speaks to humans and machines contributing in roughly equal measure. This could be considered cybernetic or cyberhuman, or perhaps a mixed initiative entity. The third dimension refers to how integral the role is in producing the experience. A high score means that the role is intended to be a consumer of the experience. That is, they are primarily a beneficiary of the experience. A low score indicates that the role is primarily one meant to create the experience for others to enjoy. Basically, this dimension asks if the role is an observer or a creator. The final dimension, agency, refers to one's capacity to influence the state of the experience. State will mean different things to different experiences, but could mean the plot of the piece, characters' attitudes towards each other or their surroundings, or perhaps the entire structure of the piece. A high score along this dimension implies a greater amount of influence over these or other areas of the experience, and a lower score indicates less agency. So to provide a sense of our process of breaking an experience down into its constituent parts, we'll talk very briefly about the roles we determine constitute the classic role-playing experience, Dungeons & Dragons. So we identified 5 distinct roles in D&D. The Dungeon Master, which orchestrates the experience, players who assume characters and explore the world, NPCs such as townsfolk, the monsters of the campaign, and skill checks, the primary system of computation of the game used to determine the results of any in-game action. So often a single person, a single human, is responsible for multiple roles. So that is the human playing the Dungeon Master also is typically on the hook for embodying the NPCs and monsters, determining the actions they take, and often role-playing as them. This brings to light an important notion of our role determination process. A single entity can fulfill multiple roles, and thus the dimension ratings are tied to the role, not the entity playing that role. When the person playing the Dungeon Master is fulfilling their duties as Dungeon Master, they tend to have high agency in that particular capacity in structuring the experience, including the frequency and ferocity of monster attacks. However, when that person assumes the role of monster, though they might have high local agency in the context of combat, deciding who and how to attack, since most monsters are not expected to survive an encounter, their general level of agency is low. Another important takeaway is that roles are experience dependent. So take Bad News and Seance, for example, as both experiences have wizards that manipulate the game world. However, in Seance, the narrative is largely predetermined. Thus, the Seance wizard is akin to, say, an actor in Hamlet carrying out scripted actions given particular cues, whereas the narrative in Bad News is strongly influenced by the wizard, as he's finding interesting narrative threads produced by the simulation and relaying them to the actor in the process of the game, in the process of the experience, among many other responsibilities as well. Now, I'd like to take a moment to describe the process we followed to create and validate these roles into dimensions. We started with a few of the source experiences we already described and attempted to break them up into roles. We then wanted to invent an n-factor model, or rather we wanted to find a number of dimensions that could be used to demarcate the roles. And our original model actually had 5 dimensions, the 4 we already discussed, and a separate dimension for characterization. We then expanded our list of source experiences to what we discussed earlier, to find roles that would hopefully find many edge cases within the dimensions. One author made a scoring rubric, and then 3 authors independently scored each role for each dimension. We then carried out tests for inter-rater reliability, and found very strong agreement for each dimension. We take this as a form of validation, as the strong correlation across our independent ratings suggests that, at the very least, our rubric is operational. So here, a score of 1 represents perfect agreement, and a score of greater than 0.5 represents strong agreement. So we can see that everything is greater than 0.5. We also wanted to ensure that none of our dimensions were redundant with each other. So we did another reliability test using the mean ratings of the 3 raters for each dimension for each role. And we found very high correlation between characterization and performance, indicating that one of them is redundant. And as we've already talked about, we simply decided to merge characterization into performance, though future iterations of this taxonomy could very well tease apart better nuances between the two to justify them being considered 2 separate dimensions once more. So, at this point, we were relatively confident that our taxonomy was capable of describing a wide diversity of roles across a wide diversity of performance-based experiences. So we then wanted to see if we could understand some commonalities between similar roles across our source experiences. So to do this, we used an Indian buffet process, which is a tool that assumes that the observed data can be described as a mixture of Gaussian distributions, but makes no assumption about the number of distributions. So this helped us to discover 8 latent features, which are the 8 columns that you can kind of see here, and assigns our roles to 19 different clusters, the different rows, based on which of the features they possess. And then, based on the roles assigned to each cluster, one of the authors came up with a descriptive name for the cluster to make it understandable for humans. And so sadly, we don't have time to go into each of these clusters in depth for this presentation, but discussing a few might be illustrative. So creative behind the scenes was the title for the cluster that contained roles that were handled by humans behind the scenes. And these have high agency, but middling performative aspects. Some of the roles that landed in this cluster were NPCs from D&D and Vampire the Masquerade, the organizers of the Monitor Celestra, and the wizard from Bad News. The creative player cluster describes roles that have a high level of agency and performative aspects. So you can see that these are players from many of the experiences that we looked at, including D&D, Vampire the Masquerade, Bad News, Azad, Monitor Celestra, as well as the spect actors of the Forum Theater, pretend play participants, the Sleep is Death players as well. And the interactive audience cluster has roles that are akin to audience members, but that have higher agency than is perhaps found in traditional pieces of theater, such as players of Seance, spectators of Coffee and Misunderstanding, and the audience of Sleep No More. So now that we have these dimensions and we have some classifications for types of roles, let's take a moment to see what this might tell us about unexplored areas of design space. Well, one quick way to get a lens into that is by revisiting the table that mentioned the correlations, of the dimensions. We see that consumer and agency are strongly positively correlated. Now that characterization and performance have been merged into one, consumer and agency is now the next highest, and a positive correlation means that as the presence of one goes up, so too does the other. And we can also see that computational and consumer are moderately negatively correlated. So as one goes up, the other goes down. Experiences which break these correlations could be considered relatively novel. So the correlation between consumer and agency is likely because a consumer with agency is, broadly speaking, a player. And players appear in many of our source experiences. So how might we imagine an experience that includes a role with high agency but low consumer? So the Dungeons & Dragons DM is perhaps the closest we have to this, but even they are consuming rule systems and rule books printed by the game designers. So perhaps a game where the game designers themselves have the ability to globally change the rules and the state of the world in real time, in mid-game, which speaks to high agency, but they're also doing so for the benefit of their player base, which would imply a low consumer score. So they're creating an experience for others, but changing an ongoing experience that's adapting to consumer input over time. And so now if we move on to computational and consumer, the negative correlation here implies that there's a lack of experiences where the machine is the intended consumer. And you know, that kind of makes sense. So pretty much all of the experiences we've described were made by humans for other humans to enjoy. But what if we inverted this dynamic? What would an experience in which a human performs for the consumption of an AI look like, where an AI is evaluating the human performance? So one thought experiment is an inverted role-playing game of sorts. Instead of the player controlling a single hero and all of the other systems of the game run by the machine, what if instead the central character or hero was controlled by an AI, and every single other system, such as NPCs, monsters, quest designs, were all up to players to control? And the goal of this game wouldn't be to beat the AI, but rather to create a nice experience for them, perhaps trying to keep them in a constant state of flow, providing them with just enough challenge that their victories fill them with fear. And the AI is evaluating the shape of its experience. The player would still have elements of consumer to them, as creating this experience is presumably meant to be pleasurable in and of itself, but this could cue some exciting directions for AI-based game design. And it's true, there is some overlap here with pet games or games like The Sims, but to our knowledge, such experiences do not demand performance on the part of the player, nor is the happiness of the virtual agents necessarily presented as the central goal of the experience, as many Sims players with swimming pools with mysteriously disappearing ladders can attest to. There's also other examples of experiences with AIs with high consumer values, such as Xylem, the ESP game, and Foldit, but we claim that these experiences give the AI low agency. So here, it's the moral equivalent of the AI going to school. Subverting the computational and consumer dimensions could yield experiences more akin to that AI going to a play. So, in conclusion, our paper presents a role-based taxonomy for works of computationally assisted performance. It has 4 dimensions: performance, computational, consumer, and agency. We shared our creation and validation process. We identified 19 clusters of common roles, and then we used our findings to brainstorm potentially exciting novel AI applications. Thank you all so much for listening. And of course, a huge thank you all to my co-authors, James Ryan, Adam Summerville, Michael Mateas, and Noah Wardrip-Fruin. My profuse apologies for not being able to be there in person, but if you have any questions, feel free to email me or again, reach out to my colleagues who should be in that very room with you at this very moment. Thank you all again so much, and enjoy the rest of EXAG. Okay, take care. Thank you.
we'll field any questions. If anyone has any. Again, we are co-authors on this.
Any non-bin specific questions?
One thing I was curious about was the interesting, like deciding what parts are roles, like they decided skill checks were their own role. And one, if you could speak a bit about how you draw that line between like this mechanic being its own role, and two, was part of the validation deciding, like each people deciding what the roles were, or like the roles you were just using scales for?
To quickly answer the second part, no, that wasn't part of the validation. That was like a brainstorming that preceded the assignment of all the values.
Yeah.
Do you want to take that first part?
For the
Demarcating,
demarcating.
I guess demarcating the rules.
Yeah, how did you choose the roles?
Yeah, so I guess it was, I kind of scooped that. It was a brainstorming session. We sort of compiled these experiences that were in this space, where the space is sort of a continual one between fully computational experiences like Mass Effect or something, and then fully non-computational ones like Hamlet.
Yeah, I mean, would it help to, do you have a paper, like to show the massive table of
That's a good
roles?
idea. Yes, we do.
Sorry. Yeah, like what's the line between like you're saying like an individual mechanic?
Like, how did you decide a skill check warranted its own role?
So,
It's not, like,
so
part of
skill
the
check is
DM.
perhaps like maybe a slightly, like, it's more just like all of the rules governing, Dungeons and Dragons. Like, that these are the different abilities that a character might have, and this is how level it. Like, it's really just skill check mostly means like sort of the underlying rule system that's governing it. What we would say is, the most computational aspect of Dungeons and Dragons. Like, it's just, there's rules, there's math, there's die rolling, like all of that, the sort of non-role playing aspect of it that's sort of getting handled, it was sort of like, we wanted to have that. And similarly for, let's say Mass Effect, like the virtual environment that you're, walking around in got its own role. Like, it's where things are, it's like, it's the level, it's where things are taking place. It's, not necessarily the things in the level. We tried to just sort of find like cohesive systems and say like, well, that would be classified as one role. It becomes harder, I'd say, with computational things, like for something like a play, we know typically what the roles are. We know the director, we know an actor, we know the audience member, we know, the GM, we know the, what have you, the dramaturg. But what does it mean in a computational system where it's all one code base? Like, what is regardless of roles?
Because the one thing that's actually kind of interesting is like a person taking on multiple roles. But how can you tell, for example, when a person and an AI agent are actually sharing a role, and this should be like a purchase one, which should you treat as a unit?
I feel like we have another. That'd be the wizard, probably.
Yeah, like the wizard.
So we tried to
why
tease-
why is the wizard separated from
the world
generator?
So the wizard is not actually like right for the world generator. The world generator happens without the wizard informed.
The wizard presses a button.
I mean, you could say that the author informs the world generator. Obviously, the coder does, but the world generator, they hit a button, the system does its own thing, spits back something out, but then the wizard is then going to operate with. So like never mind. I have nothing to say there.
So I had a question. So in the examples that you're showing here, the virtual environment is a role. For actual like physical environments, do you consider the physical environment a role as well?
Yeah. So for say like for bad news, the mise en scene, I assume the play Hamlet, we have. Oh, we don't actually have.
Yeah. So that was good.
We probably should. So yes,
we took it out because there's a few rows that are missing here. Because this took up like more than a page.
So Sleep No More, the mise en scene. We did have try to make it so that there was the analog between the analog and the digital.
So did you find that there were sort of like parallels between like virtual or like AI and like equivalent like physical?
I was gonna go like I assume that probably in the, I could be wrong, but if we look so scenery rules behind the scenes, like all of those got lumped into the same like cluster. So yes, through the the miracle of computer science, we proved that those things are But yeah, no, we did try to, yeah, that was the point of this, was to say like, well, we have all these different roles across a wide range, like how do they actually relate to each other? You know, found that some things related really well, and then, you know, the things with a single row, it's like, well, that's a very, you know, singular entity that just, you know, is not found elsewhere, like passive audience. Like essentially for the roles that we looked at, only, you know, going to a play was the audience fully passive. So.
And then with those analogs, like one thing we were interested in from the outset was turning up computation on rules that have no computation. So like what would an AI version of this rule that is played by humans typically be if it was fully AI driven? So to have these analogs between like the mise-en-scene of a play and then the virtual environment, so that's like an example of someone having done that. And then we wanted to think about that for places where it hasn't been done yet. Yeah.
I was wondering if you could talk a little bit more about your sort of examples of things that were not high computation and high cognition. So like Folded in the ESP game. So is the distinction you're making there that, so Ben in the video brought up that it's like going to school. Is the distinction you're making there that these AIs aren't getting any enjoyment out of the experience?
I think so. Let's see what Ben wrote.
So yeah, we'd have to think about.
Okay.
This is a maybe more of a Ben specific one.
I see. All right.
I think that's how we feel, but that actually doesn't bear out in the dimensions that we have, right? Because we have no like being entertained.
Yeah, like, so like right, like it's consuming, but maybe not in the way that, yeah, like we typically think of consuming an entertainment experience, which these are.
Sure, but you don't specify whether these are entertainment.
No, so that's.
Yeah, consumers overloaded, and I think we're actually alluding to like maybe that can be broken up in the part of the paper that actually talks about that. Okay. But that was kind of Ben's thing.
All right.
Yeah, might consider experience. So yeah, low agency. I think the idea, like the idea that it's consuming but also playing with it, not just consuming and like I am spitting out some number.
So then, what about interactive machine learning experiences like Andrea Tomas's cooking bot, where the player is trying to teach the agent how to cook in a virtual environment, but also giving rewards, positive and negative. You could consider maybe a positive reward is like getting some positive affect, positive enjoyment out of the experience, or would that not work?
That sounds
close,
like moving along. Yeah, moving closer to that.
Turning up consumer on that particular agent, that would be what we're talking about. Where it's not, because still it sounds like it's for the player's benefit, kind of.
Well, it's to get the agent to learn how to do the thing.
Oh, like literally to learn how to cook?
Yeah.
Like it's not, okay, gotcha, I'm not familiar with that one. But yeah, that would be a great example that we didn't know about, I think, when we were writing, or we spent in. Yeah. Any other questions? Time for lunch.
Yep.
Yep. So with that, we're going to lunch again. Lunch is from now until about 2 o'clock or so. We're going to begin here. The screen's going to stop and then kick it off again with the new lunch. So see you then.
So that was Bye-bye.